This is part of the preliminary lectures. In this part, we introduce the idea of one-dimensional space, which will be a central focus of this course throughout the year. Those of you who have been called one-dimensional man, this is your time to shine. Okay, so R is in fact the set of all real numbers. We visualize the set of all real numbers using a straight line that extends indefinitely to the left and indefinitely to the right. So here what we do is that we fix an arbitrary point on this line, which we shall call 0 for reasons that you shall see later on. And every real number will then correspond to a point on this line as follows. So if I take the real number square root of 2, this will correspond to the point that is, because it's positive, it's going to be square root of 2 to the right of 0. So square root of 2 to the right of 0, and this point will then correspond to the real number square root of 2. Likewise, negative 1, because it's negative, it's to the left, and so this will then correspond to the point that is 1 to the left of 0, which is minus 1. Okay, so in this way, what happens here is that real numbers can then be viewed as addresses to every single point on the real number line. Okay, and for this reason, because we only need a single real number in order to give a label or the coordinates of a point on this line. So for example, let's say I want to find what are the coordinates of this blue point. I just merely measure the distance, which let's say is going to be 6. Then it's to the right, so I'm going to call him plus 6. Okay, so it's a single label. So because I only need a single label to address every single point on this real line, this is therefore called one-dimensional space, because you only need one label. Okay, and because we've got every single because of this line, we can then establish order between the real numbers. Okay, and this order will be called a linear order. Okay, simply because the order is actually defined by the line. So let me be specific. So if I take any two real numbers, A and B, B is bigger or dominates A, provided, you see, if and only if, this means it's equivalent to, okay, if B lies to the right of A on the line. Okay, nothing more than that. Okay, so for example, the only reason why 0 dominates negative 1 is simply because 0 lies to the right of minus 1, nothing more than that. Okay, now with this linear order, there are certain rules which we accept without question, but it's because it's geometrically obvious, so we call these things axioms. Yeah, so let's look at what are called the axioms of linear order. Okay, so the first axiom of linear order is what is called trichotomy. So if I take any real number, okay, that will then correspond to some point on the line, then that point either lies to the right of 0 or to the left of 0, or it is identically equal to 0. Okay, and so that is called trichotomy. Now the second axiom of linear order is what is called order preservation under translation. Okay, so this is under translation. So let's say that I've got two numbers where there's order between the two. So B dominates A, okay? Then, if I translate or I add a fixed number to A and B, then the result preserves the order, okay? Even if I do a subtraction, if I take C away from both A and B, then the order still preserves, okay? This is called order preservation. Now, in order to actually make these things more clearer, it is a good practice when you read maths to put life into these symbols. So what you must do is that you must think of, okay, so for example, make AB equal to 4, okay? So 4 is then dominated by 6, okay? And notice that what happens here is that, let's say I want to shift everything up by 3. So I add 3 on both sides, so I get 7 and 9, and notice that the order is preserved. Okay, so this is called order preservation. So this is one trick you can do in order to learn and to help you to remember these formulas a bit better. Okay, so let's look at the third law. And the third law is what is called order preservation. You see, once again, order is preserved by what? Positive magnification. Okay, so let's see what that means. So what it means here is that suppose that I've got order established by the line. So B lies to the right of A, or B dominates A, okay? And then what I then do is that I consider a positive number, okay? This is very important. So I consider a positive number, okay? Then what happens here is that if I magnify A and B both by C, so in other words, I get AC and BC, then the order is preserved, okay? However, if my magnifying factor is in fact negative, okay, then what happens, unfortunately, is the order gets reversed. So you've got reversal under negative magnification. Now, so once again, let's try and breathe life into these lifeless letters by filling them up with concrete numbers. So for example, 4 is actually dominated by 7, okay? And let's say I want to scale everything up by 2. So I'm going to double everything up by a positive number 2. So I then double 4 to be 8 and 7 to be 14, and notice that the order is preserved, okay? So another way you can actually visualize this is by using a mapping diagram. So what I do is I draw the real line parallel, two real lines parallel to each other, okay? So there's my O, that's my center, the center point that I pick arbitrarily. So remember, that is why 0 is actually equal to the origin, because it's distance 0 away from the origin. So it must be the same point as the origin, okay? So what happens here is that here 4 is less than 7. So this simply means that, so 7 actually lies to the right of 4, okay? So what happens is when you scale up something, you double the distance. So 4 then doubles up to be 8, okay? So in this case, let's double up 4 to be 8, okay? So I then double 4, okay? And notice that 4 will then double up to be 8, okay? So there. And then I actually double up 7, okay? So 7 then doubles up to be 14, which is in this case here. And notice that my 14 still dominates 8 in the same way that 7 dominates 8, okay? So this is what's called a mapping diagram, okay? Where you draw the two real lines, parallel to each other, right? Okay, so what we now have here is our next law that we're going to then have is, okay, what is this, number 4, I think, okay? Then the fourth axiom, okay, or the fourth commandment that we have to believe in. Okay, so the fourth commandment or axiom is we've got order preservation by inversion. So this means that if I've got, okay, this is called, this is called positivity. Okay, let's call this positivity preservation, sorry. So if I take a positive number, any number that lies to the right of the origin, then if I take its inverse, then its inverse will also be positive, right? So it will so in other words, all the action takes part on the right side of the real line. So if I take, so in other words, if I take 0, okay, so let's breathe life into it. See, 2 is strictly positive, and therefore a half is strictly positive, okay? So if I take 2, you see, so because all the action is happening on the right side, I can just scratch out the left side of 0. So here I have the number 2. So in this particular case, then if I invert it, if I apply the inverse operation on 2, I will get a half. So this is what happens. Then I end up with 1/2 here, okay? And notice that all the outputs lie to the right of the line, okay? So in this case, so this is what is called order preservation of positivity, okay? Let's do the 5th commandment, okay? So the 5th order commandment is we've got what is called order reversal. Okay, so this is called order reversal by inversion. So in this case, suppose that I've got 2 positive numbers, okay? So this is how I write it in maths. You see, look at this, that box is specifying that both A and B are positive. So if A and B are both positive, and then I do an inversion operation on A and B, so I take the inverse, 1 upon A, 1 upon B, then notice I get order reversal, okay? So the number that was formerly closer to the origin now becomes further under inversing from the origin, okay? So so this is what's happening. So okay, so let me explain that with concrete numbers. So let's take a number. Let's say 2 is dominated by 4. So in other words, what it means here is that 4 lies more to the right of 0 than 2. It's further away from the origin. That's why you see it lies more to the right of 2. Okay. Now, when I do the inverse operation, 2 will map into a half, which is something like here. And okay, okay, so 2 will map into a half. Let's just make the picture like this. And 4 will actually map into a quarter, okay, which is here. So notice that 1/4, although 4 was further away from 0, its inverse 1/4 is closer to 0 than the inverse of 2. You see? So what inverse does is that it moves points that are further away from the origin, and then it then transforms them into points that are closer to the origin. Okay, that is this is what called order reversal by inversion. Now, notice that we have to note the assumptions. Okay, the assumption is, the reason why this assumption is so important is because both numbers have to be positive. Now we know this is not true. So for example, I know that, you see, look at this, -1 is, you see, let's break the assumption that both these numbers are positive. Now -1 is definitely smaller than 2 because it lies to the left of 2. Okay, now let's take the inverse. That's -1. The inverse of 2 is actually a half. Okay. Now you see, notice that -1 is still dominated by a half. In other words, there is no reversal. There is no order reversal as stipulated by this law. Okay. Finally, we come to the idea of what is called a non-zero square. This is commandment number 6. And what it means here is that if I take any real number and I square it, the square of any real number is actually positive. Okay. So the square of any real number is actually positive. Okay. Now, so in this case, let's okay. So for example, let's look at -2. I square it. What do I get? 4. That's positive. If I take 3, square it, 9, positive. No matter what. Okay. So let's use this thing to do our first exercise of 2021. So prove using the non-zero square that 2ab is smaller than a squared plus b squared. So if I take the product of two numbers and I double it up, that number is dominated by the sum of the squares. Okay. Now, one way to visualize this, okay, is whenever you see a product like AB, you can always visualize this as a rectangle, you see, of dimension A and B. So that's dimension A and B. So, and the product AB is actually going to give you nothing but the area. Okay. So I double up this area. So in other words, I end up with what is called as double. So the area now doubles up like this. So this is what 2AB is. Now, what happens here is that, let's say I consider the square A by A and B by B, the greens. Okay. So the sum of these two squares, so the green area, B squared plus A squared, will dominate double of AB. Okay. So let's actually prove this. Now, the way we prove this is, okay, how does one really prove these questions? What you do is, okay, let's say that I look at this. This is what I want to prove. Okay. Now, what I want to do is I want to fit it into the structure where I come up with the idea that a squared is positive, okay, or something is positive, right? So therefore, in order to fit it into this structure, I will try to put everything so that everything is rewritten as positive, okay, as bigger than or equal to 0, okay. So in this case, I can minus 2ab on both sides, and then I can therefore get a squared plus b squared minus 2ab is then bigger than or equal to 0, which is take it over to this side, okay. So to prove this, notice that proving this is identical to proving that, okay. Now I then look at this, but this a plus a squared plus b squared minus 2ab, that's nothing but a minus b all squared. Do you get it? And so, so all I have to do is I have to show that a minus b all squared is actually positive. And this follows because the square of any number is actually positive, okay? So how I prove it is as follows. So once I've got the rough idea, I'm now ready to write out the formal proof, okay? So, so what I do here is that I consider two numbers a, b, okay? These are two real numbers, right? Now, a minus b, their difference is also a real number. Okay, and in other words, so another way to write it is a minus b is a real number. Now I know by commandment 6, which is the non-zero square law, that if I square any real number, therefore by 06, if I square any real number, that square must therefore be positive, okay? But a minus b all squared is nothing but a squared plus b squared minus 2ab, and that has to be positive because it's a square of a real number, and therefore a squared plus b squared dominates 2ab as we are required to prove, okay? Right, so that brings us to the end of part 1.